Okay, so I'm recording now. Okay. All good? Can you hear me? Can you hear me? Okay. Okay, we'll try again this time. Can I start? Okay. Good morning, everyone. Okay. So today will be the last lecture about classification. And then we have a few things to talk about. So the homework 2 is due this Friday. If you haven't started, I urge you to start right now. It's really long homework compared to homework 1. And there will be no extensions. So please start as soon as you can. Okay, so today we'll just very quick recap about MLPs and ANNs. As I mentioned before, when we go to CNN, so the next chapter will be regression, clustering, and then we'll get to CNNs. And then before we get to CNNs, we'll revisit MLP in much more detail. So the homework about CNN will have, or maybe clustering, will have quite a bit of an MLP training that you will have to do. So I will get more detail about that then. But today I'll just kind of mention a few things here and there. And then I will talk about how to evaluate the performance of classifiers. This is really very important part of your homework number 2. And then I will talk about the 10 project for the graduate section. Okay, so this kind of the table summarizes all our classifiers, classification algorithms. And I will not really get into the details of this one. I ended up last time with these data sets. So yes, we are dealing with very simple one like the IRIS or IRIS data set, some California housing data sets. These are very small, kind of almost like a CVS kind of data sets. And now we are looking at these data sets, and we'll spend some time on these when we talk about CNNs. So the first one will be MNIST, and we saw this before. It's very simple digits, data sets. You can really try anything on it, and 90% of the time it will work fine because the data is not really very complicated. But it's very good to show as toy example. And then we can go to some images, like for example, the Cipher 10 or Cipher 100. These are much more complicated in terms of content and context. Okay, so when we deal with training, and you'll see a little bit of these, there is a batch size, there is an epoch, there is a round, there is validation, training, and testing sets. So what's the batch size? And hopefully I can show you some examples today. So a batch size, you have your data, right? Your training data, and then basically you really divide it into batches. So you, at every round, or every round, you input all that batch basically at once, and then you do the optimization for the whole batch at once. So, but you can imagine what's really happening if your batch size is only 1. So basically every batch has only 1 data sample. When you are doing the optimization, you'll be basically jumping around quite a bit. So maybe some data samples will take you somewhere in the gradient descent. The other one will bring you closer. So you'll be jumping around. So you'll have some kind of stability and convergence issues. Eventually you will converge, but it's not really, it's a very slow convergence. But when you have a batch size, then actually you are speeding up the convergence, and you will not really have that kind of, dancing around issue. Whenever the training model is going through your entire data for the training all at once, the entire data once, that's 1 epoch, right? So you keep repeating that because that's where the randomness is happening. So you will have multiple epochs. So this one basically depends on the learning curves. You stop it basically after a certain number of epochs. But usually we get to really kind of, I will show you some examples, a large number of epochs if you are not really converging rapidly. So, and then finally we have the round. The round basically is when we have 1 feed forward and 1 back propagation, right? So that's 1 round. So basically 1 feed forward and then 1 back propagation. there's a single round in here. Whenever we are dealing with training, then you have to split your data into training and splits. And then you take your training split and then divide it into validation and training, right? So, and we'll show you basically an example here, what's really happening. So you have your data, you do the split, 20, 80%, 30, 70%. This one basically is the test. You don't see it through the training, you don't use it through the training. This is basically what you do after you train a model and then you test your model. You take the training and then you split the training into a validation and training. So the validation, you still see it while you are training, but you use the validation just to kind of double check, am I doing the right thing or not? So that's basically your feedback mechanism. So the optimization of your gradients is really happening basically on the training set. You are using the validation during the training to double check, how am I doing, right? But now after you finish everything, you are converging, the model is finished training, then you go back and test it on the test set in here. So the test set, you have never seen it through training. That's different from the validation set. Any question about the split between these three? Okay. So there's also the learning curve. They are really early doing the training. You have a training curve, right? And then you can think of the y-axis will be the error, and then you have a validation curve. So these curves will just keep an eye on. You can say, am I converging? Because that will give you information about, do I have enough training set, right? Am I doing underfitting? Am I doing overfitting, right? Maybe the training set is not representative enough. Maybe I don't really have enough diversity in my training set. Maybe the model capacity is much, much higher than the training data, right? I'm overshooting here. Like I have too many layers, I have basically too many neurons, and basically the model is not really kind of, is not equipped to handle the data, either under-equipped or over-equipped. And in both of these, there's a problem, right? All of this you will really get to know by dealing with the learning curve. That's what I was referring to last time, babysitting your training. And there are really more tools. After we finish the CNN, then I will go back to talk about, what's the capacity of the model? How do you kind of check what's the capacity? How do you use the gradients? How do you use all these kind of tricks to double check, are you doing the right thing in the training or not? And even after you have a trained model, if you go to ImageNet and then get the trained model as it is, now you want to apply it to some of the new data. You want to double check basically, am I doing the right thing in here using this model? There are some tricks that we will hopefully have enough time, the second half of March and April, to learn these different ones. For now, I'm just throwing at you some of these terminologies, just to kind of to be aware that they exist. And then when we go to CNN, we'll get back and learn these in more detail. Here are some examples of validation and training. So this is the validation curve. This is the training curve. Keep in mind, I'm looking at the error on the y-axis. You could replace this with the performance, like accuracy or some other performance, right, on the y-axis. So now for the error, if you already starting the training, you have only like one batch or just even one data sample, right, and you are learning it, then the error usually is like very, very small, right? You just have a very small, data size. And then the validation, because really you haven't really done much training, then you're not really predicting the data in the validation set that will. So the error will be very, very high, right? As you are training more and more, then the training basically error will increase, because now you are trying to do a generalizable solution, but the validation error should really also decrease, right? And now the behavior here, where they really kind of flatten basically in here, how much gap between them, right? All of those will be the feedback mechanism that we will, between now and the end of CNN, we'll revisit basically what that means. These kind of the tools, hopefully we will learn by mid-March, what are the different things happening in here, like underfitting, overfitting, underrepresentation from the training data, and so on. All of those will be very, very handy when you are training your data set. Any questions? Yes. Cool. Okay, so let me repeat that for the audio here. So basically, the question here, the message from the training curve is that you don't want training error that's very high. You just train for a small data. Yes, if all what you care about the training error, right? But now look at the validation error. It's very, very high, right? So now you can imagine on the testing, when you apply your model, you're done. Take your model to testing data, you will have very, very huge error, right? Because you didn't really train very well. Yeah, it depends. Yeah, all those information basically are a few things. Basically, at what point both of them will start to come close to each other, right? And then at which epoch they will start trying to flatten, basically where I'm not doing any learning anymore, right? Because for the training, you see there is a slope here, right? That means I'm really improving. I'm learning stuff, right? But at the same time, if the validation is plateauing here, right, is flat, that means whatever I'm learning in here is not really doing anything for my validation set, right? So basically, it seems there is something not right here. And now another important one, how much gap between, if I want to plot this one here, right? How much gap is in between them? Is it a very, very large gap? That means basically the space I'm learning from my training set and the validation or the space representing the validation set, they are far from each other, right? So that's a problem as well, right? And you want them to be as close as possible, right? And converging together, but there will be a gap for sure. Because if there is no gap, right, then that means you are already memorizing, right? I mean, it's not general enough, right? And that's an issue. So all of these we'll look at those in more detail once to go to the convolutional neural network, and because it will have quite a bit of variety. We will revisit these curves in regression, not clustering, and the CNN for sure. We spend quite a bit of time there. Any other questions? Okay. So now there is this visualization tool that I'm hoping to include in your homework 3. Let's see if I can. Very nice visualization tool. The link is on Canvas. If not, I will double check it. So you can see from here, once you play it and you see the number of epochs that you have, you can decide on the learning rate. There's a predefined set of learning rates. The activation functions, you have 3 different ones. And then you have, if you want to do a regularization or not, you want to do basically regression or not, and then what will be the task. So for now, we just do a classification. Later on, we'll talk about regression there. There are 4 different data sets that's already predefined. This one you can see is very simple, right? There's a very easy, you can draw a line between them. This is the X1, this is the X2, right? And then very simple linear separation between them. You can really complicate this a little bit. We use this in one of the examples, this one here. Let me take this. I will be sharing the link if it's not already on Canvas, so you don't have to type it. So the other one is this one. Basically, you can see it's not really linear, right? The relationship between them. Then it gets even more and more complicated. You can look at this one here, nonlinear, linear, non-separable, right? And then finally, you have this very complicated data, right? Very, very tough to deal with. So if you start here, and then here on the left-hand side, you have the ratio between test and training. So the test, 70% is too much, actually. No, this training, yeah, okay. So 70% is training, 30% is testing. Can you see it from the back? If I can make it larger. You can see it, maybe. Okay. So there is noise. So for now, I will not add any noise. And here is the batch size. So you can go from 1 to 30. So let's just pick 10 for now. Okay. So now, what you can see, I will not really touch those ones for now. So now you can see in here, these are my features. So I want to use X1 and X2 as they are, as my features. Or I want to start basically look at polynomial, like the kernels we talked about, right? The X1 square, the X2 square, the multiplication between X1 and X2, and the sinusoid of X1 and the sine of X2, right? So these are the different features. So for now, for this data, right, it's linear. So this is x1, x2. I'm just using these. I'm not using any hidden layer, nothing. I just want to generate the data and then just run it, right? And right away, you just draw a line, right? Because it's very, very simple, basically, where you draw the line between them, right? Anything above certain value for x1 and x2, you can easily split this. You don't need any basically hidden layers to do this task, right? But now, if you do the same thing for this kind of data, right? So I can see you are not really, look at how many epochs, 300, 400, right? And look at the test loss, it's 0.5, training loss is 0.5. I'm stuck, because I'm not getting anywhere, right? I'm just trying very, very hard. I don't have enough. Where's my mouse? I don't have enough in here. Tell me basically, look at this one here, that this means from there, I'm splitting my space. This one will be one class, and this is another class. If I go to the x2, which is in the y-axis, that means I'm splitting this y-axis in here. This is one class, this is another class. That's all what I have, right? So I'm getting 2,000 and 3,000. You will not really get any learning happening there, okay? But now I can start to see if I can bring my kernels, x1 squared and x2 squared, right? And see basically if I can learn something from here. Still, right? Not much happening, right? I can increase my features. Let me use everything, right? Why not? I'm learning, right? Because all my features in here are giving me enough information to really divide between these, right? And you can start to hover the mouse on top of each one of them until you, this one is splitting it this way, this splitting this way. By the way, how much saturation you have in the colors in here in the backspace. So this actually I should have mentioned. So what you have in here, these are the data, right? This is basically the orange one means to one class, the blue one for another class. The background, it means how the learning algorithm is really trying to split the space. The more saturation you have, that means more confidence, right? Here, there's not much confidence, right? In between these two. So now, if you look at the x1 square, this how it's splitting, x2 square. Look, x1 times x2, that's where basically you're starting to learn quite a few things. And this one. So if I remove the sinusoid, let me see if I can learn something here, right? So basically, the feature that's really giving me quite a bit of information is the product between x1 and x2, right? So that's what we're talking about. You have to, for the last, not last, I mean, 30, 40 years, we spend a lot of time trying to basically manufacture these features, right? We try to take the signal, try to understand the physics behind it, come with math, come with the features, and then now we are trying to rely on the neural network to do everything for us, right? So let me now go to, I will disable these features. I want what you have to keep in mind, CNN or neural network in general. Remember when I was talking about early on, what is the really difference between classical AI or machine learning and then the new machine learning? Before we used to literally made up these features, right, and input them. But now we're trying to make the neural network itself learn these things. It has to learn these features early on in the training. So if I remove this and then introduce a hidden layer, and then it's not bad, right? Not bad. You can see the test loss, not even 500 epochs. We are getting to really 0.01. And then from here, you can start to basically, I'm just using x1, x2, and the algorithm itself tries to kind of figure out basically what these weights are. So if you hover the board in here at the mouse, then you have basically these are the weights, right? So positive and negative, these are the weights for each one of these, right? Let me start it here, right? You can really click and just double check the testing data. These are the testing data. So when you say test loss, that's basically how much error I have in the testing data that's really highlighted in here, okay? You can decide to make this threshold. Basically, you really want to have class 1 and class 2. You don't really have anything in between, so you have to have threshold the area in here. You could do that. confidence either basically above 0.5 or less than 0.5. But we don't really usually do that. Any question about this? Okay, if you repeat this, and I don't know if this will work or not, let me test it. With just a batch size of 1, and let's see what's really happening. It's fine. It's working beautifully there. Okay. So now if I add some noise, right? You can see the noise, this was having the data, right? So this is some noise. You can see there's quite a bit of orange ones in the middle here. You have blue ones out there. Let's see basically what I'm doing. Not bad. Yeah, I missed few of them, right? But I'm general enough, right? If I'm not really general enough, then these things will start to, like the border will include them. That's not really general enough. So this is not bad. Now let's see if this will work for a more complex data. Let's see if it works for this one here. Oh, let me remove the noise. Increase the batch size. Yep, not bad, right? Like still within 400. It took longer, right? I mean, now almost 700 and not even 0.01, right? Yeah, so you can see like almost 1,000 epoch. I'm not even there 0.01 as in the previous case, but it's still working fine. Okay. So increase the noise. So let me do the batch size first. Still works fine. You see that? Did you see that? Basically how the shaking? That's basically each one. See this one here is happening. The boundary is basically because I have only one single data point, right? So it keeps shifting quite a bit. That's because I'm using this one for each batch. I'm just using one data point. So it convert basically slower, but that's fine. Let's see if it works for the complex one here. It's very, very tough, right? 500, 600 epochs. You can still see the error. We are really plateau, right? Yeah. That means what? That means basically this network in here, it doesn't really have enough capacity to figure out basically the higher order description of this data, right? Any question? Yes. Oh yeah, imbalanced data will be a problem, right? Yeah, when you have imbalance, there's a big issue actually. As we mentioned, like in the multi-classification problem, it will be an issue in balanced data. And I think when we talk about transfer learning, I think we have a small exercise how to deal with imbalanced data. After we finish, there's a transfer learning lecture, and we'll talk about how you deal with that. But yes, it will be an issue. Let's see, add another hidden layer and see basically if we are improving this or not. $400 still, right? Stuff, right? Not much happening, right? Like you see this learning curve plateauing. I'm not really learning much, right? And keep adding. So we need more capacity, right? Look at the learning curve, right? Let's wait. I don't know. I'm trying this I don't know if this will work or not. Let's wait. Nothing, right? 1,600, 2,000, nothing, right? Nothing is happening. So we'll wait more. Look at the gap between them, right? Not enough, right? Not enough data. Let's wait. Yep, they're not going anywhere, right? So now what about if I increase my input, right? And do this. Same problem, right? There's some variations. Let's see if that works. Look at the gap. Look at the training loss. Getting there. Still problematic, but it's getting there, right? If I add noise, this will not work, right? I mean, if you look at these ones here, right? These are very dangerous areas, right? Okay, so using the same thing, let me just increase just a multiplication. See, we're getting there, right? It's working. And now if I add the sinusoids, so this was 1,600 epochs. Let me add everything, right? Yeah, I'm at 800 and I'm already doing a really good job there. Yep. I need to increase my batch size, right? As soon as you see these things, right? It means I have to increase my batch size. This is the capacity of the model is much higher than my batch size. So now let's try, yes, go ahead. If it's converged basically and then plateau after some time, then yes, that's fine. But if you have underfitting or overfitting, then that will not, you can increase the epochs, it will be the same behavior for a long time. So you should stop it. So yeah. Okay, so how is the question is how does a batch size affect the training? So imagine now a batch size, I'm splitting my data into batches, right? So the batch size, I input this, so my X will become that batch, right? If it's only one sample, right, then I'm doing forward back propagation, I'm doing the optimization, I'm changing the weights based on one sample, right? The alternative, I have 10 samples or 50 samples. My X is concatenation of all these 50 samples. I'm inputting these feed forward. I'm doing my back propagation. I'm optimizing my weights based on 50 samples, right? So I can imagine from 50 to the next 50 samples, I'm converging basically my gradient, my weights are changing more basically, less radically than if I have one sample to the next sample. Because if your next sample is very different from the previous sample, then you're really jumping around, right? So that will take basically the error, you know, at this behavior that you saw before. Okay. So let's see if we can increase. It's for free, right? So we can just do this. Is there enough capacity in the network to learn without inputting the features? Right? It will take longer if it can handle it. What do you think? Will it be able to handle it? Look at the curve, right? We are stuck at 0.5. Right? Something happening. 1,000 epoch. Anything? Now, if you look at while it's still running, just look at what's happening. So this one here will tell you how is this neuron here is looking at the data, right? If you look early on, this one is basically looking at this way, this one the other way, this one the other way around. And this one, there is some variations. As you go higher and deeper, you start to see basically that's where the context of the data is. Am I learning much from this here? Or am I just basically having a much higher capacity than what my data can handle? And that's what's really happening in this case. I'm not really doing much in here. But now if I use this for, let's do this one here. Right? Do you expect this to work fine? Right? This is much simpler data, right? Nothing is happening at 1,000 epoch. So why, if you look here, and stop it here. So why am I'm not learning much here? So what went wrong? What went wrong? What do you think? I have very basically expensive neural network, right? I mean, I have 4 layers. I have 4 neurons on each layer, right? Why didn't it work? Making it more complex will not. Yes, go ahead. At which neuron? At which layer? Especially the lower, the shallow, the deeper ones, right? The deeper ones. The deeper ones basically are not really trying to split. Is really, they're not really doing much, right? They're really. This is where the capacity of the model is much higher than what the data actually needs, right? So you're really over fitting in here. That's really not really working very well. So if I reduce this, if I can do this. Right? I was to place my 4 layers with 2 layers, and it works really well. Okay. Now remember, when you have 1 million parameters, right, and your data is not enough to optimize this for 1 million parameters, right? The data is not really enough to give you enough space, then you are always stuck at the local minimum somewhere. You're not really getting the solution. But now reduce this 1 million by half, and now you have 500,000 of these parameters. Your data dimensionality is capable of making you optimize for these 500,000 parameters. That's when we'll refer to this later on. You know, what's the capacity of the model? And all of this will happen after we finish the scene. But for now, I just want to, get you to play with this tool. What else? And what else? Maybe we can add, maybe this one here. Just add some noise. You see the test loss is 0.3, right? The training is 0.2. These are the noise, right? You have quite a bit of errors in here. Is this a generalizable model or not? Remember when I was talking about generalizability, robustness, right? If it's not generalizable, if it's really overfitting, if it's really memorizing, what will happen? It will try to include these ones, right, as well. But now we remember when we talk about SVM, we are adding that capital C factor to allow certain values to be on the other side of the margin. Same thing here in your network. We're really trying. Okay, it's fine to have these errors in here, but on the overall, we are really capturing the subspace. Okay. Any questions? Yes. The cost function, yeah. So overall, as you are increasing, if I do this for a smaller batch size, I'm not sure if this will work or not. It's just one sample, right? This should be jumping up and down at a certain stage. Maybe not. No, it's not. Okay. So as you are optimizing, right, you're having your data, right? Now you are already calculating how much difference between your hot vector and your y hat, right? And you are back propagating, right? So all what you are really worried about, basically, you are at this value in the loss, and you want to basically reduce it to the next one with the learning rate, right? And you keep doing that, like how you go through the data once, that's one epoch, next one, second epoch, and so on, until you are reducing it quite a bit. Now, while you are doing that, you are not doing a good job for every single sample. And that's the whole point of generalizability. You are not really optimizing this for every single sample. That's why probability-based, basically, you are missing these ones, right? And that's basically what we mean by generalizability. We need to allow it enough capacity that basically is not really tuned to every single sample. And this is very good because we know these samples have noise. So now, are you learning the noise, or are you learning the subspace that's governing the data, right? And this is basically an example where you want it to be general enough, not to be optimized. There's an example. Let's see if I can come up. So if we do this, we'll add quite a bit of noise. Reduce this capacity. I don't know if this will. Maybe I reduce it quite a bit. Yeah, still it works fine. Yeah, there was an example, I forgot which one, where you start to see basically the boundaries becomes like around this one. So it's basically is memorizing more than learning. Maybe I have to reduce this to 1. I forgot how I get this. Yeah, it's not doing a good job here. Yeah, I don't think I can regenerate that one. But it basically, it will really kind of try to really include those noisy ones into the boundary, which is really a wrong thing, right? We don't want that. So you'll have this link in here. Of course, I mean, you can really, we haven't touched any of these. Like we changed the learning rate, the activation functions, the regularization ratio. All of these you can really change those. So we haven't touched those yet. Okay. We revisit this when we talk about regression as well. Any question about this one? The challenge actually will be when you have a different network, right? Even as simple as AlexNet. After the model is out there, can you figure out if it's really working the way you want it to work, right? And why, right? And hopefully we'll spend 2 lectures, hopefully in April, about what kind of visualization tools you can really build. Like GradCam is one of them. There are some contrastive learning, other one. Yes, he was first. Yes, go ahead. Okay. Yeah, because basically there's the nonlinearity, right? So the question here, if I do this, so what did you do? Linear, and then? Okay, 3. Oh, 4, oh, 4 neuros each, okay. That's it? Is that? This one? That's it? Yeah, so what do you think will not work? So this one doesn't work, why? All what we changed, the activation function is linear. So why it doesn't work? Yes. Exactly. So the activation function itself, basically, remember that's where the magic happens, right? So the nonlinearity, right? Other than that, everything is linear. W times X plus B, right? So now the nonlinearity coming from the activation function. If you remove that from activation function, then everything is linear. So now this data is nonlinear. So you're not learning the nonlinearity in the data. Let's try it. Good work. Yeah, any of them, even any of them, there is nonlinearity in it, right? Because you cannot really describe the output in a linear fashion for the input. All of them as nonlinear, except the linear one, right? And now, which one works with which application? That's actually a different subject. But the important thing is to remember, the nonlinearity in the neural network is really coming from the activation function. That's extremely important. If you take that out, then you cannot learn the linearity in the input data. Right? That's very important. Yes. Okay, so the question is, if you're really dealing with data and you cannot easily visualize it, because this is very easy. This is two-dimensional data. You can visualize it, you can figure it out. And that's basically where there are different ways. If you know where the data is coming from, the physics behind it, right? And you understand basically what the physics governing the data, right? And you start to have some hypotheses about the physics behind the data. Then that's when you start, figuring out what will happen. In general, we don't really want to manufacture features. You want to keep that to the neural network to figure it out, right? You don't want to manufacture what's really happening inside. Now, what's really it becomes more of a trial and error, the number of layers that you have, the number of neurons in each one. But what will happen after you finish this course? You will not really come with an architecture from scratch. You will go basically to a model that's already out there, right? A model like we have tons of them. We'll look at 4 or 5 of them in this course. The simplest one is AlexNet, for example, right? MLP is one. MLP means is a fully connected layer, right? It's a fully connected layer. That means every neuron has an input from every single neuron from the previous layer, right? That's an MLP, fully connected layer. There is no convolution whatsoever. There's no C in N. There's no C in here. So this is the simplest one, right? And now you start to kind of MLP, of course, is not really the most, and we'll see why it's very, very expensive compared to CNN, right? Now you go to CNN, you have AlexNet, you have tons of other ones, right? And ResNet and so on. And then each one of them basically have already a predefined architecture you can just use as it is. Now, if you get into the research side to come up with a new architecture, that's basically where the whole art comes into play. But as a user, you will use one of the existing ones. And even if you have a project like outside this course, then you have to, use a trained model, right? I mean, a model already trained, and then try to use that one, and then just transfer, basically change the last, and we'll have a homework about this, change the last layer to transfer to your new data. So for example, we have a geophysics data, right? But we have, network that's already trained on ImageNet, completely different data. You take that model, change the last layer, transfer the learning to this new geophysical model or geophysical data, and then it will work. I mean, more or less. Not always, but it works. That's how we do it as a user for the model. If you want to create architecture, that's a different story. Okay. So we can see reload doesn't really give you quite a bit. Okay. Let me grab this up. Okay, let's look at the performance evaluation. So we've got cross validation, precision recall, confusion matrix, and ROC curves. Okay, hyperparameters in performance evaluation. So usually, like we have K and M, we have the capital C in SVM, the number of layers, the number of neurons in A and N's, and that's basically where you have, this is the hyperparameter, tuning, right? And then it just basically, these are the different control parameters that you really need to use to control your algorithm. These ones, you don't learn them, right? You don't really have a mechanism within the training to learn these models, these parameters. That's why we call them hyperparameters. You predefine them, you try, and then you try and error. But usually there is a knowledge in a certain data, like in audio, speech, financial data. There's a general basic kind of knowledge in the community about, yeah, people tried, and this is the best K or the best C or the best, architecture to use. But this, you don't really learn them as a hyperparameters. You don't learn them in the process. These are different from W and theta and B, right? You see the difference between them? The W's you learn, right? The C and the K and the number of layers, you don't learn them in here. So the first one is really cross validation. That's basically how you do it. And this is very, very important in the project to really look at that. So basically, you have your training data, right? So you can really hold this as your testing or as your validation, train on all this, test on this one, and you keep changing which batch or which data module is your testing. And then you just average overall. That becomes basically your cross validation. So this is really, you must be familiar with this task. Now, let's look at this example. You have 10 questions. This is the answer key, and these are basically the answer of a student, right? And now this in here is the grading, right? So check mark means correct, X means it's wrong. If you take the accuracy, right? The accuracy means the number of corrected label sample divided by the total number of samples, in this case, 70%, right? But now back to the imbalanced data problem, right? If basically in your data, if 90% of the time it's always true, right? And somebody says, okay, I will just answer everything is true, right? Then the accuracy is what? 90%, right? But that individual basically knew nothing about the material, right? So accuracy is extremely dangerous, and there are some really good papers out there that they use accuracy as the measure. Very, very dangerous, because it doesn't really tell you the whole story, right? Do you see the why, everyone? Why accuracy is really bad, or not enough measure, not like bad, but not enough. So now we look at, I'm very sure you have seen this before, true positive, true negatives, false positive, false negative diagram. So it depends on what and we'll look at these in different ways. But in this case, I'm looking at the prediction on the Y in the columns, the actual, the ground truth on the rows, right? So now the true positive, I'm predicting the correct ones, which are really actually positive. The false positive, these are actually negative, but I'm predicting them as positive. And then the predicted, I'm predicting these as negative, but they're actually positive. So these are false negatives. And finally, the true negatives, I'm predicting these as negatives, and they are actually negatives, right? So everybody familiar with this diagram, right? Yes? No? Any question about this diagram? If not, this is a good time because I'm going really fast now. Okay. So now you start to mark each one of those. So this one here is false positive. This one is true negative. This one is true positive. So it's correct, and it was correct also in the, and so on. So basically, you start to mark these. And now we count with these measures: precision, recall, and F1 score. So this diagram in here, right? I'm looking at these diagrams in here, and then I'm picking, I'm choosing whatever inside this circle here as my true, as my predicted positives, right? But among them, these are true positives, right? But these are false. The ground truth is, but I picked these as positive. So my prediction that these are positive and these are positive. I did a good job here, I did a bad job here, right? But at the same time, I did a bad job here, right? So I didn't really pick these as positive as well, right? So now that's where basically recall and precision come into the picture. So if you are a visual person, this is one way to look at what's really precision. I'm looking at the ratio between this and this, meaning that how many of my selected items are really relevant, meaning that I'm looking at how many of those are really truly positive. So now I picked all of these as truly positive, but only the ones on the left-hand side as truly positive. In other way, I picked all of these as truly positives, as predictably positive, but only the left ones are positive. That's the ratio between TP over TP plus FP in this case, which is 60% precision. Okay, so this is really good measure when the false positive is very, very risky, right? And you can think of the easiest way, at least for me, to take this as diagnostic in medical conditions, right? Is it okay to predict somebody basically has a cancer, or miss that somebody has a cancer? Very, very dangerous to miss somebody has a cancer. But if you predict somebody has a cancer, then you can do more tests and then you figure it out later on. So that's basically kind of it depends on the application. Some applications really, it doesn't really matter. So it's all based on the application that we are referring to in this case. Okay, so now that's precision. The recall now, the recall is looking at this whole thing in here, right? And I'm looking at how many of the relevant items, right, are selected, meaning from the truly positive ones, all of these, how many of them I picked as positive, right? So I'm looking at the true positives, right, divided by the true positive plus the false negative. What are the false negative? These are the false negative, right? These are the false negative ones. These ones in here, right? So in this case, I have 75% recall. So one, there's F1 score, there's F2 score. It's just combining these two together. So putting the precision and the recall together into one term. But really what I really want you to remember, what's precision, what's really a recall in this case. Any question about precision and recall? You will deal with this in the homework too as well. Question? It's clear. Yes, question? Maybe? Okay. Okay. Now, what if I have multi-class, right? I have two classes here. I have apple, orange, mango. I have this, my prediction class. I flipped it, right? I mean, I have the true class in the columns. Because I don't want you to stick to only what I had in the previous one, right? So in here, previous slide, I have predicted in the column, actual in the row. But sometimes some references online, you will have the predicted in the rows, actual. Doesn't really matter as far as you know what you're doing. So now, we'd like to look at basically, if I have three classes, let's look at one class at a time. So if I'm looking at the class apple, how do I doing to really classify my data as apple, right? So now, the way you do this, you have this box here, right? Right? This is basically, I'm predicting these as apples, and they are actually apples. And then everything else, it just collapses into one class, right? So basically, these two together will become one class, non-apple, right? These two in here will be non-apple. These four altogether will be non-apple, right? Right? So now we have 2 by 2. Let's look at this. So what are the true positives? I have a 7, because that's what I predicted as 7, and they are really actually 7. So that's TP is 7. What about the true negatives, right? What are the true negative ones? The ones that I predicted as non-apple, and they are truly non-apple. Which ones? These ones, right? So I have 2 plus 3 plus 2 plus 1. That's basically 8 is my true negatives. Do you see that? Everyone? Yes? Okay. Now, the false positives. What are the false positives? Basically meaning I'm looking at the ones I predicted as apple, right? I predicted as apple, so I'm looking at this row, but they're not really apple. That will be 8 and 9. That's 17. False negatives, those are the ones I'm not predicting as apple, right? Which these 2 rows, but they are truly apple. So this is 1 and 3. So that's basically 4. And now precision is really 7 divided by 7 plus 17, that's 29%. And the recall is 64% in this case. And the F1 score is 40. And now I do the same thing. I repeat this for the orange class and then for the mango class. And now I have precision and recall for each one of these classes I have in my data set. Okay? So now I keep doing this, but now if I do this for the MNIST data set, so now can you imagine as I'm learning, I'm looking at the prediction label. This is my predicted label. MNIST, I have 0 to 9 did it, like 0, 1, 2, 3. And then the y-axis, I have the true labels, right? So now ideally, what you want to happen? You want to have basically very dark here. This is a barcode in here, meaning 0 to 1. This is an intensity, so 0 to 155. This is the saturation, this is basically the highest value. 0 means is white. So now, if I really doing extremely good job, then I will have a diagonal here of a very, very dark color, like black, right? Everything else is white. That means I have 100% predict, basically accuracy and classification in this case. So it keeps iteration 1500, 1600. So it's getting, there is an improvement, right? So this is another way to look at your classifier to say, am I moving in the right direction or not? I have some errors, right? That's fine, but I'm really moving in the right direction here. But now, one way to look at this, and I will look at this in more detail in a minute, but let me just pause it here. Oops. Okay. So now I'm looking here. Which one get darker much faster? So I have this one here, these two. So that will tell me what? What does this tell me? I'm looking at the digit 0, the 1, the 6 in here, and the 8, right? They became darker much faster than the other ones. What does that tell me? Yes. Exactly. So I'm doing a better job in here, easier for me to figure this out. It's not the same basically for number 2, 4, the 9 is problematic as well, because the 9, I'm looking at the 9 as a 3, right? At this iteration, as a problem, right? So I'm really very, very far off. I'm looking at the 5 as an 8, right? That's a problem, right? So I keep doing this. I don't know if this will work. Okay. So 2000 is improving. Yep, I'm improving quite a bit. So this confusion matrix in here, if you're gonna do it only for a single digit, that's what we have on the right-hand side. It's for a single digit for 5, and then for the rest is non-5, right? That's a single digit. So that's what your confusion matrix in this case. But now we do it for the whole 10 classes, then you will have something like that. It doesn't matter how many classes you have. The confusion matrix is the same concept in here. Any question about the confusion matrix? Yes. This is for basically for every round, actually, for in this case. But it depends, right? I mean, you can do it for every epoch because you go in the data just once or at once. That will be better to do it. So I believe this one is for every iteration. Around, I think. Okay, so now let's go to the next thing that we haven't talked about, right? So now, imagine that you have, these are your predicted classes, right? And you're looking at digit 5 is your class, right? So everything else is non-5, right? So now, on your score, right, you have to come up with a threshold, right? Remember in the visualization, there was a thresholding, right? You have to decide on the threshold. Is this a 5 or not a 5, right? At the classification, you have to decide on those, right? So now look at this. This is basically my predictions, right? So now if I use this threshold in here, and I'm saying whatever on the right-hand side of my threshold is I'm predicting everything on this side as 5, everything on this side as non-5, right? So now if you look in here, I'm looking at the precision here. How many of them is really 5? I have 1, 2, 3, 4, 5 of them, right? Is it 5? 1, 2, 3, 4, oh, 6. 1, 2, 3, 4, 5, 6, right? So 6 out of the 8 is 5. That's precision of 75%. But look at my recall, right? I picked all the 6 5s as 5s. So I have 100% recall, right? I go to the extreme case, I'm here. So everything in here is 5. Everything in here is not 5. So if you look at my precision is 3 out of 3, 100%. My recall dropped to what? 50%, right? So now you have to have a trade-off between precision and recall based on the threshold. So if you draw the x-axis is your threshold, and then the y-axis is your precision and recall. That will be the curve, the green one for the recall. This one will be for the precision, right? So they're going against each other. So now you have to decide how we can pick the threshold for this behavior, right? And the way we do it, this is one way, is to really plot precision against recall, right? And you can see basically you're already dropping quite a bit in here. And usually a general rule is you look at the 80% when you have the recall, and then just before drop, right? Just before drop, you pick this one here to be your threshold value. That's kind of just before the recall, the precision dropped quite a bit. But you don't want your recall to be very low, right? You don't want to pick one here. That's really a very bad decision to do. Okay. So if you are really working in the homework assignments or in the project, especially in the project, I really want to see basically how you pick these threshold values in your project. Okay, finally we have the ROC curves. So the ROC curves, basically this is a way where you can look at, you bring the sensitivity and the specificity into the picture. And these are very well known in the medical field if you're already working in the bio-related application. So the sensitivity, as we define in the right corner, bottom corner, is the ability basically to really correctly identify patients with a disease, right? So that's extremely important in the medical side. On the other hand, the specificity in this case, can we correctly identify people without that disease, right? So both of these are really important. So now, the first one is the TPR rate, so TP over TP plus the false negatives. Another one is the false positive divided by the sum between FP and TN, the true negatives in this case. If you plot these, so we have the false positive rate, right? This is the FPR. This is the one specificity in this case. And then I have the TPR, which is the sensitivity over recall in this case. What you want this to be to go very quickly to 1 as soon as possible, right? And then basically flatten out and here, right? So basically what we're really desiring for the area under this curve to be equal to 1, right? Under this one to be as close to 1 as possible, right? And the best way to understand what's really happening is this case. Look at this toy example. The left-hand side, I have an area curve of 100%. What we are really saying in this case, the negatives and the positives, they are disjoint, right? There is no overlap between them, right? So basically now I can easily differentiate correctly between my negatives from my positives, right? Completely. So I can look at this distribution as completely non-overlapping in this case. As soon as I start to drop less than 1 or 100%, then there is some overlap. So that means for most of the negatives and most of the positives, I can correctly identify from each other. There are some of them here, some cases where I cannot be identified from each other. These are very close to the support vectors or the boundary decision, the decision boundaries that I'm looking at in my classification. So this one, I'm going to keep it basically as small as possible. Now, if you are at the 50%, basically at this 45-degree line here, that means you have no mechanism whatsoever to differentiate between the two, the positive and the negatives. They're overlapping completely. Basically, it's become just flipping a coin, like it's a 50% chance. Flip a coin basically and is the same performance as your algorithm in this case. If basically you get something lower than that, 45 degree in here, then basically that's what's really happening. There is something wrong in the whole classification that you are doing. Flipping your ground truth or something along those lines that's really happening in this case. So now you have all of these. If you're doing classification, you have to look at all these different ways to evaluate the classifier. Yes, question. That's basically where the precision recall come into the picture. So when you have at the very end, right? When you have your vector, right? Your probabilities, you have to decide basically which one you pick to become is just the highest one. You have to have a threshold one, right? Yeah, if you have the softmax, yes. Exactly. In that case, basically you missed, if it's a true answer, then you just missed it, right? Just what we had in here, in this case. If I'm here, right, I'm picking this as non-5. So I missed that, right? That's the wrong one. So now in that case, I'm really lowering my recall, but I'm improving my precision. Yeah, I mean, you pick this one to be a non-5. Your output is classifying this digit as non-5. Yes, that's your output. Right? And then you repeat again, and then for different threshold, and now this becomes a 5 if you move threshold to here. And now how to decide which threshold, you plot the curve like this one, right? For each data point in this curve is a different threshold. So each one here represents different threshold. You plot for a different thresholds in here, right? What you're doing this. You're changing your threshold values. And instead of really plotting them this way, you just plot the precision versus the recall for every single threshold that you have. And now you go to say, just before the precision had dropped quite a bit, I will just pick that's my threshold. So now I pick this one. So now you have some balance between recall and precision. You mean as this one here? Yes. Oh yeah. So So in that case, basically, this is the ideal case, the one on the left-hand side, right? This is the worst that you can really do, right? This means there's something wrong with your implementation. In most of the cases, you are here. You're going to pick the threshold basically that will give you as much separation as possible, the smallest overlap as you can, right? And that will depend on the data that you have, right? It's not the same for every single data set that you can change, right? Okay. Just a quick note about the imbalanced data, right? We were asking about that earlier, imbalanced data. So if you look at, we will look at this in more transfer learning later on, but for now, if you look on the left-hand side, basically you have area under the curve is around 92%, right? But if you look in the one on the right-hand side in here, right? What we have one class is 95%, and the other negative class is only 5%. So quite a bit of imbalanced data. And basically the behavior of the precision to the recall, you can see it, we're expecting it to be like this, right? To drop in much smoother. But now you can see it's dropping is almost like in a linear fashion, right? And that's just because of the imbalance in the data. So now right away you can say, okay, there is something wrong with my data. I have to go back and change that, right? So they really tell you quite a bit, not only about the performance, but also about the imbalance in your data if you get such curves, right? And then finally, I want to look at this this confusion matrix again. The left-hand side is really the ideal case, right? Or almost ideal, or what the best we could hope for MNIST. The one on the right-hand side is basically, imagine that one of your classifiers, right? But even this one is enough feedback about your data. So if you look at what are the two digits I'm confusing the most, what do you think? Which two digits I'm confusing the most? If you look at, if I'm in here, I'm just flipping things, right? I'm putting the 0 and 0 really perfectly, right? I'm looking at the 3 and the 5, right? There's a problem here, 3 and the 5, right? What about the 5 and the 3? You can see this one, right? So the 3 and the 5, I'm really confusing them together, right? So now I have to go back and what? Maybe I need to add more digits or images of digit 3 and 5 into my training, right? That's one feedback. Something wrong in my algorithm to differentiate between 3 and 5 in here. If you look at the rows, right? If you look at the rows, which ones have too many highlights? Like the first one, 0, is very, very good, right? I'm not confusing it with anything, right? But if you look at the 8, I'm confusing the 8 with quite few of them, right? Right? I mean, the 1, the 3, the 5, a little bit the 9, right? I mean, I would say the same thing about the 9 and the 5, right? And maybe this one as well, the 2. So these ones compared to the 7, the 4th, the 1st, and the 0th, they're fine. But the other ones, I'm confusing more and more of these, right? And now the other thing is this 8 and 5? Let me see. Yeah, let's look. This is I'm confusing the 8 with the 5 in here. I'm looking at the 5 and the 8, right? So compare this one to this one, right? They're not symmetric, right? So the way I'm confusing 5 with 8, I'm confusing 8 with 5. They are not the same way, right? So that's another way to look at this, right? So am I more biased to the 5 or to the 8 in my confusion? But they're not symmetric in this case. There's quite a bit of confusion matrix you can really use to go back and rechange your data set. But these are the most examples. So what else? Yeah, the 8 and the 9 still, if you look at these columns in here, still they are really illuminated everywhere. It's not the same way in the other columns. Any question about this confusion matrix? Yes. Yes, so the Y basically is the error. I flipped these. Basically, if it's very, very dark, right, it's 0, that means I'm predicting this correctly. If it's 1, if it's white, that means I'm doing this incorrectly, right? So basically means I'm doing very good job predicting the 0 as 0, the 1 as a 1, yeah, maybe the 2 and the 2 as well, 3 and 3, right, 4 and 4. But now the 5 and the 3, I'm doing a very bad job here. Same thing, 3 and the 5, right? So these two are, I'm doing a really very bad job. So if you have enough budget to add data, right, I would focus especially on 3 and 5, right, followed by these two. Yes. Yeah, it's the other way around. Yes. depends on what you want to do. Okay, I already want to spend 5 minutes on the project. So let's go through, read it. Okay, so this is for the graduate class in here. So what we have is this, is the classification problem. You have OCT data. So this is a data set that we published a few weeks ago in Europe. So you have OCT data like this from a true patient through a clinic in Houston. And then we have a severity level, right? This is severity level is very well known in the eye medical side. DRS severity. We have 3 classes, 0, 1, and 2. This is what you need to do. Come with the classification one. So it's simple enough, but at the same time, the data is really, really hard. Don't wait until March to do this. One of my students, Chen, he created basically, if you go to Zenodo, you can download the data. And then there's 2 types of data in there. You only stick to one of them. So you don't really deal with the other data. So only deal with the prime data. You can see this one here. Please don't make that mistake. Only deal with the prime data, not the tricks. The tricks is a different data set. Okay. Now he provided this spreadsheet that has all the split between test and training with the ground truth. So you can use that for your training and so on. What else? He provided the data loaders. You don't really have to use the data loaders. This is the code. If you really want to create your own or use your algorithms for other data modalities, you can go to this tutorial for data loaders. But he drafted this one specifically for this data. This data loaders in here. You should be able to download this data. So now, again, what we are expecting is the following. I'm expecting that you have to at least have 4 different methodologies to classify, right? So a CNN with different architecture is still one CNN. But you have to have a totally different algorithms. None of them, or not all of them, should really work very well, right? It's fine. I want you to really get your hand dirty with different classifiers and just try to see if it works or not. Everything on the table. If you really want to pre-process your data, post-process your output, from A to Z, basically, whatever you want to do. As far as you do what we have here, I'm fine. So any processing you'd like to do is fine. As far as you justify it in the report, I'm fine with that. So now, teams, I look at, you can be, I really encourage you to work in teams of 2, not more than 2, right? Unless there is a very solid reason. If you have odd number of students, then we have to figure that out at the end. So now there is a tool in Piazza where you can team up with other people. So the Atlanta section student can team up with the distant learning students and vice versa. If you don't really have a team member, just look at Piazza and then you'll be able to team with somebody, hopefully. Now, the performance evaluation, I'm looking at the very, very comprehensive performance evaluation. Just don't limit it to one only. As many of these performance evaluations that you can really put together. What you have in homework too, you have quite a bit of these codes. Just write them as your project evaluation metric. I mean, from now, you use them, they give you the visualization you need, and then you have that part already covered from homework too. We will have, maybe at the bottom here, we'll have progress report on March 10th. And this is just, it's very simple one-pager. The only purpose of this one, I just want to make sure that you, by that time, you read these 3 pages. You already teamed up with somebody. You already have your names on the progress report. Tell us basically what you are thinking, what algorithms you have been doing. Only one pager. I just want to make sure that you really did something by March 10th. The final term paper is due on April 14th. Together with the presentation file, and then the teams will present in the last 2 lectures in here their presentations. Only 7 minutes plus 3 minutes for Q&A. Questions? Yes. Only for guys students. Yes. Any questions? Graduate students students who are in the graduate sections. just in case. Okay, we'll see you Wednesday. Thank you.